In today's episode of Surds Part 1, we'll be looking at surds, what they really are, the rules of surds, simplifications of surds, and of course, we'll be doing some exercises. Surds are numbers that do not have exact values. Numbers such as the square root of 2, the cube root of 7, the square root of 8, the fifth root of 25, etc., etc. These numbers have values that their decimal are not ending and could be repeating. Surds are numbers that are classified under irrational numbers, and this is a feature of irrational numbers. When you use devices to look for values of surds, they give you just approximate values. For instance, if you look for the square root of 2 with a calculator that is 10 digit, a 10-digit calculator, you get something like this: 1.414213562. You look for the square root of 3 with the same calculator, you have 1.730, 1.7320, 50808. You do the same for the square root of 5. You have 2.23, 606, 7977. Now, when you look at these numbers, there's something about them. They all get to the limit of 10 digits because I'm using a 10-digit calculator to look for this value. For this, you have one. For the square root of 2, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it's the same for all of them. So if we could get a device that can give us 15 digits, 20 digits, 40 digits, and so on, you will get values ranging to the limit of these devices, and that is the feature of surds. And it's somehow irrational to use figures like that in your calculations. That is why you have this aspect of surd in mathematics. So surd is a good thing, but we must understand how we use them. For this series of lessons, we'll be looking at quadratic surds. Now, quadratic surds are just square roots. So the purpose of this lesson will not go beyond, the scope of this lesson will not go beyond square roots, surds that do with square roots. So we'll be looking at surds like this: the square root of 2, the square root of 8, the square root of 7, the square root of 3, the square root of 5, the square root of 11, the square root of 11, and so on. So let us get to the rules of surds. The rules of surd. For you to be able to calculate well, you must be able to apply the rules of surds. Now, the first rule is this: It says that if you have the square root, we are dealing with quadratic surds. If you have the square root of a times b, or we write it like this, the square root of ab, this is equal to the square root of a times the square root of b. Have this at the back of your mind. Rule number 2. If you have the square root of a divided by b, or written like this, the square root of a over b, this is the same thing as the square root of a over the square root of b. Now there are certain things that are not included in the rules or so, but I'll put them as my own rule, so it will help us in calculation. I call this number 3. Rule number 3. If you have the square root of a plus b, this is not the same thing as the square root of a plus the square root of b. Rule number 4. If you have the square root of a minus b, this is not the same as the square root of a minus the square root of b. Once we know these rules, we will be able to do our calculations in surd without problems. So let us start. The first thing we are going to do is simplification of surds. Simplification of surds. Surds that can be simplified are surds that have perfect squares in them as factors. The idea of simplifying surd is trying to bring out a perfect square as a factor from the number in the surd. We have examples here which I'm going to solve. So in simplification of surd, let us take them one after the other. For a, we are asked to simplify the square root of 18. Root 18. Now we know that 18 is the same thing as 2 times 3 times 3. We know 3 times 3 is 9, which is a perfect square. So our root 18 is the same thing as the square root is the same thing as the square root of 9 times 2, as you can see here. So this will give us the square root of 9, or root 9 times root 2. This will give us 3 root 2. So our root 18 is equal to 3 root 2. For b, root 45 our 45, we have to break them down, break our 45 into prime factors. That is just the key. 45 is the same thing as 3 times 3 times 5. So our root 45 is equal to the square root of 9. You know, our 3 times 3 is 9. That's the perfect square. Times 5, which is the same as which is equal to this root 9 times root 5, which is equal to 3 root 5. C. This square root of 405. Recall, we are breaking our numbers into its factors. 405 is the same thing as, now if the number gets bigger, all you need to do is just start dividing. Now we start with the least prime factor. Can 2 go in 405? No. The next prime factor is 3. Can 3 go into it? Yes. How do we know? Any number divisible by 3, the sum of its digits must be divisible by 3. So 4 plus 5 is 9, and 9 is divisible by 3. So we start 3 times 3 in 4, 1. Remainder 1. 3 in 10, 3. Remainder 1. 3 in 15, 5. Now let us divide this 135 again. Can 135 be divided by 3? Yes. We go 3 times 3 in 13, 4. Remainder 1. 3 in 15, 5. Can 3 go in 45? Yes. You continue like this until you have no way to continue again. So that will give us 15. 3 in 15, yes. Then the next prime factor is 5. You can see that I have here, I've broken 405 into I broke 405 into 3 times 3 times 3 times 3 times 5. So we have 2 perfect square. Yeah, 9 and 9. So this is something as 81 times 5, or we say 9 times 9 times 5. So the square root of 405 will give us the square root of 81 times 5, which is equal to the square root of 81 times the square root of 5, and this will give us 9 root 5. D. We have the square root of 363. Now 363 is equal to the square root of 3 times 11 times 11, which is equal to the square root of 121 times 3. I hope you know that 121 is 11 times 11. This is equal to the square root of 121 times the square root of 3. This will give us 11 root 3. Whenever you are simplifying your surds, you must note that your surd, a particular surd, could have more than one perfect square as a factor. So what you do is you get the highest perfect square.